Hey physics students, here's solutions for chapter 15, numbers 1 through 130. Just kidding, 1 through 13 odd. And first one, we've got an object undergoing simple harmonic motion takes 0.25 seconds to travel from one point of zero velocity to the next. So the first thing we got to process is this is the signature of motion here. So 1 point of zero velocity, that would be horizontal tangent lines here. So what we have to realize here is that 1 point of zero velocity to the next is half the period. So if this takes 0.25 seconds, then the period is 0.50 seconds. If you didn't get that right, and you're wondering why you didn't get the following parts, then you should stop here and go fix those parts. So B, what is the frequency? Frequency is 1 over period, so that'd be 2 hertz. And C, what's the amplitude? Well, they told us from here to here, those points are 36 centimeters apart, so that means the amplitude is half of that amplitude. Just like for trig functions, we're talking about the same thing. It's the distance from equilibrium to that extreme point, so it would be 0.18 meters, or 18 centimeters. Number 3, what's the maximum acceleration of a platform that oscillates at an amplitude of 2.2 centimeters? Convert that to meters just because, and a frequency of 6.60 hertz. So that means the period would be 1 over that. So let's see, we do 6.6 and we have a little inverse button right here, x to the negative 1. That's 0.152, sticking with their sig figs here, 0.152 seconds. All right, now what do they want to know? They want to know what's the maximum acceleration. All right, let's see if we can figure that out. Now I know that the period is equal to 2 pi over omega, right? Which means omega is 2 pi over t. It's basic algebra, you can switch those. So that's 2 pi over that. And you know, while we're doing that, it's also omega would be equal to 2 pi. Since 1 over t is the frequency, it's 2 pi f. That's the same thing. So let's do it that way. 2 pi times 6.6. Why do I keep doing that? So omega is 41.47. And what the units for that be? The units for angular frequency, that's what we call this. Right? Angular frequency, it's just this constant times f. So that would also be in inverse seconds. Because 2 pi, that's just a radian measure, ghost units. You could say it's radians per second if you want to, that's the same thing. So that means, if you think about the way that these functions work, position would be equal to amplitude, 0.022, times, let's say it's a cosine function, that's what we usually do, omega 41.47 t, and the velocity would be equal to, that would pop out one time, and it's a negative sign function there. And acceleration negative 0.002. This would pop out again, so now I have 41.47 squared times the cosine of 41.47t. So what's the maximum acceleration? And you could get all fancy if you wanted to and say, I know how to do calculus, maximum acceleration, find the derivative of that, set it equal to 0, or you could graph it, or you could just say, you know what, this is a trig function, cosine, that just goes between 1 and negative 1, regardless of what's in here. So the maximum value is just the amplitude. The maximum value of a sine or cosine function is its amplitude. So that's 0.022 times 41.47 squared. That's 37.8 meters per second squared. So I mean, that's a fact that maximum acceleration, I'd write this over here. So observing what we did in that problem, maximum acceleration is going to be is the amplitude times omega squared. I don't think that's the kind of thing that you necessarily want to memorize. It's just kind of built into what we're doing here, but it is a fact. So number 5. In an electric shaver, the blade moves back and forth over a distance of 2 millimeters. So back and forth over a distance of 2 millimeters. That would mean the amplitude is 1 millimeter, right? And in simple harmonic motion with a frequency of 120 hertz. That's the frequency of, the frequency of alternating current is 60 hertz. That's when you plug in a light bulb, if there's it seems like there's almost like a tiny flicker going on that you almost can't realize is there. That's because alternating current, the electricity is changing direction with a frequency of 60 times per second, or 60 hertz. So it's twice that. So frequency is 120 hertz, which means the period, if we wanted to know, well, just for practice, I don't know if we need to know this or not, is 0.0083, or 8.3 times 10 to the negative third seconds. We want to find the amplitude, maximum blade speed, and the magnitude of the maximum acceleration. So kind of similar to number 3. So same idea here. If x is equal to a cosine omega t, then velocity is equal to negative a omega sine omega t, and acceleration is equal to negative a omega squared cosine omega t. And it's straight out of your notes. So they want to know, what's the amplitude? We did that already. Amplitude is 0.001 meters, or 1 millimeter. For B, what is the maximum blade speed? So the velocity max is a omega, right? Or the same logic that we used in the last problem. So amplitude 0.001 times omega. Oh, we didn't find omega, did we? So omega period 2 pi over t, or 2 pi f, either one. Since they gave us the frequency, we can do that. It's 2 pi times 120. If this is like starting to make a little bit more sense now from what you were doing before, it's radians per second, or just inverse seconds if you want. If this is making more sense now, this would be a good point to pause the video, maybe revisit some of the other homework problems before you keep watching this. So a omega, that give us let's see, hold on, I don't like my answer here. I seem to be off by a couple decimal places. Why did I get 0.75 here? Oh, I sorry, I see what I did there, sorry. So that's 2, sorry, that's wrong. 2 pi times 120 is not this, it's 7.53 times 10 to the second inverse seconds. Sorry about that, I had a number hanging around in my calculator. Maybe you saw that, you probably saw what I did. So we have this, then that number times omega, times the amplitude rather, 0.001, so that gives me 0.75 meters per second. And then the maximum acceleration is a omega squared. And that's, just multiply that same number by another omega, which is 753, and that gives me 568 or so meters per second squared. Right? Not too bad. Okay, so number 7. Loudspeaker produces a musical sound by means of the oscillation of a diaphragm whose amplitude is limited to 1 micrometer. So 1 micrometer is 1.0 times 10 to the negative 6 meters. And we want to know at what frequency is the magnitude A of the diaphragm's acceleration equal to g. So let's see if we can figure that out. So they want to know at what frequency are we going to get the maximum acceleration equal to g. Well, I know that, let's see, if we set g 9.8 meters per second squared equal to, I know the maximum acceleration is a omega squared. So that's a times omega squared. So we can solve for omega here. I'm going to do that off screen here. So 9.8 divided by 1 times 10 to the negative 6. Want to see what I'm doing? Fine. Is equal to that. And then I'm going to take the square root of that answer. And that gives me an omega of 3,130 radians per second, or inverse seconds, because radians are a ghost unit. And they want to know what's the frequency associated with that. And then I know that by these equations up here, that omega is equal to 2 pi f. So f would be equal to omega divided by 2 pi. So there's my omega, divide that by 2 pi, and that's about 498 hertz. That's part A. Part B, for greater frequencies, is A greater than or less than G? So let's figure that out. So what happens to A if we increase F? What was the relationship here? So A was equal to amplitude, this is the A max, equal to A omega squared, right? omega is equal to 2 pi f. So if we substitute in here, we could see that the A max is equal to A times 2 pi f squared. So if you increase the frequency, that's going to increase A, because A is directly proportional to the square of frequency. So that will be greater, or an increase. Number 9. The function x equals 6. Let's see if I can write this. So x equals 6 meters. It's our amplitude times the cosine of 3 pi radians per second t. That's my omega. That's A. This is omega. Plus, so there's a shift here. This is a horizontal shift, or what we call a phase shift. Problems like this. Plus pi over 3 radians per second. So maybe I'm just going to pause there for a second and think about what is the effect of doing this. Well, that takes what was a nice cosine function that just started at its maximum, and now it starts somewhere else. So we can handle that, right? We know our trigonometry. What are the displacement, velocity, acceleration, and phase of the motion? And what are the frequency and period of the motion? So a bunch of, just basically answer every question you possibly can about this. So A, what is the, at time equals 2 seconds, they want to know what are all those things. So at time 2 seconds, let's see if we can do this without a calculator. So 2, if I plug 2 in here, I get 6 pi, and 6 pi is a multiple of 2 pi, so to see where I am, I can throw out multiples of 2 pi, right, because it's just going to repeat itself over and over again. So that means I'm at whatever cosine of pi over 3, that's 1/2 times 6, so that would be 3 meters. You could use your calculator for that, but that's what it is. For B, what's the velocity then? So let me find my velocity function. I'm going to take the derivative of that, so it's going to be a negative sine function per the chain rule. The derivative of what's inside, that's 3 pi, so that's going to be 18 pi out here. And then the inside will stay exactly the same, 3 pi t plus pi over 3. Leave the units out for that. And they want to know at 2 seconds here, so by the same logic, this is just a multiple of 2 pi when I plug in 2. So it's just the sine of pi over 3, which is square root of 3 over 2. So the velocity is going to be negative 18 pi times the square root of 3 over 2. So let's see what that is. That should come out to be about negative 49 meters per second. Part C is the acceleration. So another 3 pi is going to come out. That gives me negative 54 pi squared times the cosine of 3 pi t plus pi over 3. So once again, plugging in 2 here, that's just 6 pi. So that's the same as cosine of pi over 3, which is 1/2. So that acceleration is going to be 1/2 of this coefficient, negative 27 pi squared. And let me just put that in my calculator to make sure that I'm agreeing with the book. That's negative 270-ish. And that's the acceleration, sorry, so that's meters per second squared. Cool. Part D. What is the phase of the motion? So when I plug 2 in here, let's see. Actually, I think what is the phase of the motion? We're not really going to talk about that, so I think rather than go into how to do that, I'm going to leave that part and say, just skip that part about the phase of the motion. You can look at that in the book if you want to, if you're interested, but that's not something that I'm going to ask you and not something you're going to see on the AP test. So we are typically not going to see things with phase shifts. But if you do, I mean, it's a trig function, so you know how to do that. And we also want to know what's the frequency and the period of the motion. This is the frequency and the period of the motion. So I know that period is equal to 2 pi over omega. So omega is 3 pi, so 2 pi over 3 pi, well, that's 0.67. I don't need to do that. Oh, and I think, did I do this backwards? I think this is F, sorry. And then E is the period, or the frequency, rather. So then, if the period's 0.67 seconds, if I flip that over, instead of 2/3, it's 3/2, so that's 1.5 seconds. Right? Number 11. Here we got a block on 2 springs. So there's a spring on this side and another spring on this side. So just to understand what's going on here, I'm going to make a force diagram. Let's say it's been displaced a little bit off to the left. Then, so if this is equilibrium here, when it's here, this spring over here is going to want to go back toward equilibrium. Right? So there's a spring force there. And this spring here will also want to go back toward equilibrium. So the effect here, if you have one spring on either side, this is like having twice as much force. So the force is equal to negative 2 kx because there's 2 springs. Right? They're working together. They're both trying to restore toward equilibrium, so we have twice as much force. We have Fs equals kx from each one of the springs. And once we know that, I think everything falls into place there. So the block, so actually, to say one more thing about that. So this is like having one spring with a spring constant of 2k. So that means they're looking for what's the frequency of oscillation. I'm going to find the period first. I know period of a mass on a spring is 2 pi times the square root of m over k. So that's 2 pi times the square root of, the mass is 0.245 kilograms. And the k, it's really twice what they say the k is. So, because we have the 2 springs there, so that's that 7580 times 2. And I just need to jam that all into the calculator carefully. 2 pi times the square root of 0.245 over 7,580 times 2. That gives me 0.025 seconds, but I was looking for the frequency. So I'm going to flip that over, x inverse. That gives me a frequency of about 39.6 hertz. And last one. An oscillator consists of a block of mass ½ kilogram connected to a spring. When set into oscillation with an amplitude of 35 centimeters, the oscillator repeats its motion every 0.5 seconds. That's a T. And the mass was also ½ kilogram, right? And the amplitude is 0.35 meters. So they want period frequency, angular frequency, which is omega, spring constant, maximum speed, and maximum magnitude of the maximum force on the block from the spring. Okay, so that's a bunch of stuff, but all easy to calculate. So A is the period. So didn't they just give us that? Why are they asking for that? I guess because they said it repeats its motion. Maybe that was supposed to be tricky or something, but not. Okay, so B, what's the frequency? Frequency is 1 over period, so 1 over 1/2 is 2 hertz. C, they want to know what is the angular frequency. Angular frequency is omega, which is either 2 pi over T or 2 pi f, whichever you want. So 2 pi times 2 is 4 pi, which is about 12.6 radians per second, or just inverse seconds if you want. E, oops, there's another letter in between there, D. A, B, C, D, E, sorry, I gotta sing that sometimes. What's the spring constant? So you think about a relationship here that we know that would involve the K. I know that period is equal to 2 pi times the square root of m over K. And I think that I know everything here except for the K. So let's practice here about solving. I'll try to solve this for K. So squaring both sides. Look, there's another 4 pi squared, just like Kepler's third. M over K. So K would be equal to 4 pi squared m over T squared. Definitely not the kind of thing you would even remotely think about trying to memorize. So let's see, 4 pi squared times the mass, which was 1/2, right? Divided by the period, which is also 1/2 squared. And that gives me a spring constant of about 79 newtons per meter. And then E, what's the maximum speed? We saw that in earlier problems. Vmax is equal to the amplitude times omega, because that's the amplitude of the velocity function. And that's equal to, so amplitude times omega, 0.35, times what we just got there. So that's 79, 79, where did that come from? 27.6 meters per second. second. Wait, they don't have that. What did I do? Let's see. That's the amplitude times, oh, I just multiplied by the spring constant. What the heck? Sorry. Let's try that again. I was double taking there because that is the correct answer for F, so we'll have to revisit that. So amplitude, which is 0.35, times omega, which was 12.6. That's about 4.4. And then the last part, which we accidentally just got the answer for, what's the magnitude of the maximum force on the block from the spring? Well, as this thing oscillates back and forth from here to here, the maximum force, because spring force is equal to negative kx, the maximum amount of force you're going to get is when this is maxed out. And that happens at the ends. That's when you have the maximum. That makes sense, right? That's when the spring is stretched or compressed the most. So the maximum of that is equal to k times x max. But x max is just, that's another way of saying amplitude. So k times the amplitude is about 27.6 newtons. And that's it. So not too hard, that stuff. That's the basics of simple harmonic motion.